In this video, I will be deriving the equations we will need to simulate the height of the liquid in these three interacting tanks. So we have three rigid tanks lined up and they are all connected at the bottom. So there will be a free flow between tanks 1 and 2, and I will define that as Q1, 2. So it's the flow rate between tanks 1 and 2. Similarly, we'll have a flow rate between tanks 2 and 3 at the bottom, and I'll call that Q2, 3 for the flow rate between tanks 2 and 3. We'll also have a flow rate coming out of the bottom of tank 3, which I will call Q3 for the flow rate out of tank 3. So since these tanks are rigid, they have a defined cross-sectional area. So the cross-sectional area for tank 1, I will call A1. For tank 2, it's going to have some cross-sectional area, which I will call A2. And tank 3 will have some cross-sectional area, which I will call A3. Each tank will also have its own height of liquid. So there will be a height of liquid 1, height in 2, and then a liquid height in 3. And I have called these H1, H2, and H3 respectively. So now I'm going to start to define the flow rates between each tank. So for tank 1, it is just going to be the flow rate between tanks 1 and 2 is equal to some proportionality constant times the square root of the difference between the tank heights. So it'll be the square root of between the height of tank 1 minus the height of tank 2. So I put this in absolute value bars because we are taking the square root of it, raising it to the 1/2 power, and so this will ensure it's never negative. So now for this flow rate, we'll have to define the direction. So for this problem, I'm going to define the direction from 1 to 2 as positive. So to do this, we will use sine. So instead of just having this expression, the flow rate between tank 1 and 2 will be equal to the sine of the height of tank 1 minus the height of tank 2. So when the height of tank 1 is greater than 2, this will return a positive 1 and our flow rate will be positive. When the height of tank 2 is greater than tank 1, this will return a negative 1 and our flow will be negative because it will be in reverse. So we're going to see the same thing with the flow rate between tank 2 and 3. It will be the sine of the difference between tank 2 and tank 3 times a second proportionality constant times the square root of the difference between tank 2 and tank 3. So that is our expression for the flow rate between tanks 2 and 3. Now let's create one for the tank, or for the flow rate out of tank 3. This will just be proportionality constant 3 times the height of tank 3 to the 1/2 power. So now we have our three flow rates in between the tanks defined. We are going to define a flow rate into the second tank. I will call that Qn. And we are going to use this flow rate into the second tank to adjust for a set point of tank 3. So additionally, we'll also have some set point for the height of tank 3 that we want to reach. And I will call that H3 set point. And so we are going to be using a proportional control, which is the simplest type of control, to adjust our flow rate into the second tank to reach our desired set point for the liquid height in tank 3. So how we're going to do this is the flow rate into tank 2 will be the proportional gain which is represented as Kc, which is just a constant, times the difference between the set point that we want to reach and the actual height of the liquid in tank 3. So now we have all of our rates defined. We need to, we want to simulate the heights. So how we're going to do this is we are going to use the relation of the volume in the tanks. So the volume in the tanks, the change in volume of the tanks with respect to time will be equal to the flow rate in to the tanks minus the flow rate out of the tanks. So we just have to write the derivatives for each of the tanks. So this will give us the volume. So let's start with the volume, the rate of change of volume in the height of, or in tank 1. So the change in volume for tank 1 will be the flow rate N. Well, if we look at our tank, there's no flow rate into tank 1. And then our flow rate out is just the flow rate between Q1 and Q2. So I can rewrite the change in volume as the change in the cross-sectional area times the change in height, because the area times height will give us the volume of the tank, and since height is since the cross-sectional area is constant, we'll be able to pull area out of our derivative. So our equation will be the area of the first tank times the change in height will be equal to the flow rate, the negative flow rate between 1 and 2, which is the flow rate out of this tank. So using the same thing, we'll have the change in volume represented by the cross-sectional area times the change in height over time will be equal to everything in to tank 2 and everything out, all the flow rates. So our flow rate in to tank 2 is Q in. We will also have the flow rate from tank 1 coming in, so the flow rate between tanks 1 and 2 will also be going into tank 2. And then we'll have the flow rate between tank 2 and 3 going out of tank 2. So we'll subtract that. Here is our flow rate for, or our equation for tank 2. Now we need to write the equation for tank 3. So again, the rate of change of the volume, which is represented by the cross-sectional area times the change in height, will be equal to the flow rate N, which is the flow between tank 2 and 3, minus all the flow rates out, which is just the flow rate out of tank 3. So now we can transition over to Python, and I will be able to use these equations to simulate the heights of the liquid in each of these 3 tanks.